So most of this module is going to be work, but we're going to end this module with a discussion on recursive data structures. So we are going to talk about specifically a linked list and how that can be made into a recursive data structure. I'm not going to bother writing the list, but the reason we bring this up is because trees, which will be in the next module, are recursive data structures. And it's just simply a good way to start thinking about it, right? It's not just functions, but we can think of structures themselves recursively. So if we redefine a linked list, then we can look at the linked list as a collection of nodes that every node has itself and what comes after it. Not another node, but the head of another linked list. So, right, I'm the head of my own list, but the guy after me, he's the head of his own linked list. So a linked list is either empty, it has a node called a head, and it's a reference to the next linked list after it, right? The last node, he just points to null, which is an empty list. So here with so that's the way to think about it, right? I've got myself, and then after me is another slightly shorter linked list, right? Right. It's kind of that idea of a sublist, but, made a bit more explicit. So a linked list recursive class would look like this, where we have a public linked list, and it's got a private node head. The size method, what would that look like? Well, this would be the helper method here, and here's the wrapper method, or rather, here's the recursive method, and this is the wrapper method, the method that we're going to use to call it. So to calculate the size, I return the size of the head of the linked list. And if the head is null, return 0. Otherwise, 1 plus the size of the linked list starting at head.next. So, right, this calls the size of the linked list starting at head. And this will return 1 plus the size of the linked list starting at head.next, which will call the next one after that, and so on and so forth. To do a toString, right, here's the wrapper method. Simply convert the string starting at head, or convert the string that starts at node head. Then here, string head, if the head is null, return a empty string. Otherwise, return head.data plus a new line, and then convert into a string using the toString method the linked list that starts at head.next. Head, what we just go through is that we look for if we're going to replace, so notice this is slightly different than set. What we're going to do here is we're going to replace all instances of an old object with a new object, right? We start the head, and basically we say, well, the head is not equal to null so long as we're not the end of the list, if the old object is equal to head.data. So if the old object or if the head has the old object in it, replace it with the new object, and then replace all instances of the old object with the new object in the linked list that starts after me. Now, this is as you saw on the slide, the Lisp programming language is a recursive language. It deals with this kind of list and this data structure. So in some languages, this is the way to program things. And there's nothing wrong with programming this, especially if you want to get a better feel for the way it works. So how does add work? Say we want to add to the end of a list, right? So we're not going to look at a specific index. So here's our wrapper head method. If the head is null, we just simply make that guy the head. Otherwise, we want to add the data to the end of the linked list that starts at head. Okay? So let's look at that void method. We want to add data at the end of the linked list that starts at head. If the head is followed by an empty list, let's create a new node and place it at the end, or place it after me. So, right, if I've got an empty list after me, then maybe fill it up with somebody. Otherwise, I'm going to tell head.next, I'm going to tell the guy after me, the list after me, hey, add this to the end of you. Add this to the end of you. Finally, cancel. That happens sometimes. I'll probably have to cut this out. And finally, the remove method. That's a bit trickier, right? What we have, if we want to remove some specific data, here's our wrapper method. If the head is null, right, we can't remove anything because it's an empty list. Otherwise, if the head actually has it, we just simply move ahead. Otherwise, we want to remove out data from the list starting here, and this is how we got to that list from head. So here's the head of the list. So I want to remove this out data from the head of the list, and this is the predecessor of that list, right? The way I got to that list. If we're at the ending point, return false, we couldn't remove it. Otherwise, if the head contains, and head here, right? So it's important to understand here, head in all these cases refers not to head of the list, of the whole list. It's this specific node, which we are the head of this sublist, so to speak. So if you didn't get that earlier, maybe go back and evaluate now and charge that, right? This is the head of the sublist, and this is how I got to that sublist. So if the head of the sublist contains this data, then I tell the person who got here from me to skip over me. Pred.next is equal to head.next. Otherwise, go on to the next node. When we go over the trees, I'll go in over a lot more detail, but this is just generally the way that it works here.